So mean or average values. Here is a curve, and let's say we're going, well, according to this diagram, we're going from this point on the curve to this point on the curve. So the question is, what's the mean value for y between these points? So a mean value. Y is changing between this point and this point. So that we could do some sort of average value to represent y. This could be the average voltage if this was representing voltage up here. How do I find the mean value? Well, if you think about what the area underneath here represents, if I find the integral, I'm finding the area underneath this curve. So if I consider that now not to be a curve at the top here, but a rectangle, and draw in a rectangle here, then actually the area I've just found, oh, that's good, the area I've just found, the area I've just found, let's try and do it like this. So I draw the rectangle like that, assumes that it's the base is length x, which is this bit, and y will be effectively the average value, won't it? So if I find the area underneath this curve, this whole area here, it's the same as the area for a rectangle with the same width but height, average value. So what I can say is that the area equals x times some average value for the y, and this bar means average value. Rearranging it, the average value for y must equal the area divided by the x. What's x? It's the distance between my limits, a and b. And written in an integral, what that means is the mean value equals the integral under the whole curve, which is the area, so that's this bit, divided by the width, x. So that's this bit. And so written as an integral, that's all that's saying. It's using the fact that finding the integral between the points a and b allows me to find the area under the curve. So if I divide that area by those limits b minus a, I'll end up with an average value for y. And that's how it works. Instead of saying divide by b minus a, I can say multiply by 1 over b minus a, and that gives us this familiar function, or this familiar form of this to find the mean value. So effectively it's 1 over the top limit minus the bottom limit multiplied by the integral between those two limits of y with respect to x. So if you want to make a note of that, that's the formula that we use to find the mean value here. So let's look at a new problem here. Now, with whoever takes you for the maths when I come back, he's going to be looking at some numerical methods to find the area under the curve. So this might well be one of the methods he'd use. There's Simpson's rule, the trapezium rule, the mid-ordinate rule. There's quite a few different ways to find the area under the curve by a numerical method, which means you don't integrate it, you just do it by dividing the thing up into strips and working out the area altogether by finding the area of each strip, as you'll see. Sometimes you need to do that way, especially if the function is very complicated or if you don't even know what the function is. But anyway, so let's have a look at finding the mean value of this function using integration. So we use the formula y bar, the mean value of y, equals the integral between 0 and 3, because our limits are 0 and 3, look, of the function 3x squared plus 2 with respect to x. And then we divide that by, or we multiply that by 1 over the top limit minus the bottom limit. And so that's what this average value formula tells us to do. Find out the integral and then divide that effectively by the limits. 1 over 3 minus 0 is just a third. What's the integral of 3x squared? Right, 3x cubed or just x cubed plus, good, between the limits 0 and 3. And so that's a third x cubed plus 2x between 0 and 3. Work out what that is, which equals 11. Now, what is that? That is an average value, y bar. If I were to plot this, just to show you what this is telling us, if I were to plot this function, here it is, you might have expected this curve, actually y equals 3x squared plus 2, some sort of quadratic. What we're saying is, if I were to put this into the notes, so we can see it, between 0 and 3, what we're saying is that between these points, 0 and 3, which is here, so this particular region here, then the average value for y between those points is 11, the average value. So if I was plotting force against distance, or velocity against time, or voltage against time as something is changing, I can calculate what the average voltage is during that 3-second period if this was describing the voltage. A very useful thing to do, to come up with an average value. What do you do to come up with the average value? You just integrate between the limits that you're interested in and then divide by those limits, and that's all you do, and it gives you the average value. Okay? If we look at curves over a complete cycle, here, for example, then we find that it actually averages out to be 0. And so if we square x, though, we get rid of the negative values, and we get the bottom curve then becomes positive, so actually this switches up to there, and we get this. Okay? So if I now find the average value of that, then I can get a value for the mean value for the voltage, say. So if I want to know what is the mean voltage over a complete cycle, it's no good doing what we just did and integrating between 0 and 2 pi, a function like this, because it'll come out to be an average of 0, which is what you'd expect. Agreed? But I want an actual value for the voltage to represent the voltage. So what I do is I square everything so that I get an actual value for this voltage. So I square everything, find the mean of that, and then finally at the end to square root to get rid of the fact that I squared it. So I find the square root of the mean of the squared values, the root mean squared value. So RMS is to do with that. And I'll leave you to have a look at the textbook and see how that works. Okay?